No, we might want to get our x2 of t function. And you might think, okay, well, x2 of t is going to be 1/2 at squared, because we start at 0. And here's your acceleration, about 30 centimeters per second squared. That's off by a little. It's a little less than that. Yeah, probably 28 or 29. You got to be careful because that wouldn't be right. Because this one doesn't start at t equals 0, and you don't really have a t equals 0 velocity because it wasn't moving at t equals 0. You could still extrapolate to get what the velocity would have been at t equals 0 and so forth, but we're going to do something a little differently. First of all, we're going to say x2 of t is for the motion of this second object, and it doesn't start till 1.7 seconds, and it's over at 6 seconds. That might not stop moving at 6 seconds, but it's no longer moving with this acceleration. Presumably it hits something or starts falling. Something happens at the end of the ramp where you can't assume that it's still following the same position function. Okay, this doesn't have the same acceleration, something happens to it. And that's certainly the case for what we did in lab. So the x2 of t has a domain, t domain, that goes from 1.7 seconds, which is when it starts, because remember we defined in this ellipsis, we didn't really say it, we implicitly defined t equals 0 to be the time at which the first object starts. The second object doesn't start till then t equals 1.7 seconds. Okay, well, I do a little auxiliary variable. Tau is t minus 1.7 seconds. And then if you do x2 versus tau, you find that x2 is, now I've got the wrong number here. It's going to turn out to be about 15 centimeters per second squared times tau squared, because the acceleration is 30 centimeters per second. When tau equals 0, the velocity is 0, because when tau equals 0, t is 1.7 seconds. Okay? So, we have this, where tau goes from 0 to 6 minus 1.73 seconds, 4.3 seconds basically. And this is equal to 15 centimeters per second squared times, well, tau is t minus 1.7 seconds. And now the domain is from t equals 1.7 seconds to 6 seconds. And don't be distracted by the fact I put a 1.73 here and a 1.7 here, and I also had a 1.732 here. Use the right number of significant figures, but be consistent, so I'm just going to take the 3 off there. Okay, well, that would be your x2 function. And we can expand that. That's 15 centimeters per second squared. Now, t minus 1.7 seconds squared is negative 3.4 seconds times, well, okay. I'll square this. Okay, if you use precise numbers, this is what you get when you square this. You can verify that. I'm pretty sure that's accurate. 17 squared is 289 and so forth. So that's what, 15 centimeters per second squared times t squared. Same acceleration, the half the acceleration is the same. Acceleration is still 30 centimeters per second. 3.4 times 15 is what, 45 and 6. So that's minus 51. Now, seconds times centimeters per second squared is centimeters per second times t. And then 2.89 is almost 3. That would be 45. This is about 3% less. 3% of 45 is a little more than 1. I'm going to say that's plus about 44 centimeters per second squared times second squared is centimeters. You can check my arithmetic. But that would be motion of the second object. Again, 1.7 seconds less or equal to t. less or equal to 6 seconds. Well, that's the form 1/2 at squared plus v naught t plus x naught. Meaning, the motion is the same as that of an object that started 44 centimeters down the incline with negative 51 centimeter per second velocity at t equals 0. And that would have reached the t equals 0 point at t, the x equals 0 point at t equals 0. But it didn't because it wasn't moving at that time, and that t equals 0 time is not in the domain, so that doesn't matter. But if you wanted to have the object, say on a parallel incline, if you wanted to start it at some point on the incline with some velocity so that it would hit the 0 point and start rolling down at the time the second object got to the 20 centimeter position, no, you could interpret it and you could easily see, okay, started upward with a 51 centimeter per second velocity from a point 44 centimeters down this ramp. It would work. So, think about what I just said. Okay, I think that's all I want to say about this.